When we previously explored the characteristics of mechanical waves, we found that two traveling waves can add together constructively or destructively as a result of the superposition principle. Constructive interference occurs when two identical waves are superimposed in phase so that the amplitude of the resultant wave is the sum of the individual waves. Destructive interference occurs, on the other hand, when the two identical waves are superimposed exactly out of phase so that the amplitude of the resultant wave is the difference between the individual waves. However, sustained interference is only possible when the sources are coherent, meaning that the EM waves maintain a constant phase with each other, as well as being of the same single wavelength. That is, the sources are monochromatic. Light from ordinary sources, like a fluoro lamp, is incoherent in nature as well as consisting of many wavelengths, so we don't see interference from these sources. Light interference was first demonstrated by Thomas Young in 1801. He used sunlight that entered the room through a pinhole in a window shutter. With the aid of a mirror, he then projected a beam onto a screen containing two slits placed side by side. Light passing through the slits was then allowed to fall onto a projection screen through observation. He observed that when the slits were large, placed apart and close to the screen, then two overlapping patches of light formed on the projection screen. However, when he reduced the size of the slits and brought them closer together, the light passing through the slits and onto the screen produced distinct bands of colors separated by dark regions in a serial order. Young coined the term interference fringes to describe the bands and realized that these color bands could only be produced if lights were acting like a wave. As the light passed through the small slits, the waves passing through interfered with each other, much like the ripples of a pond. The bands of light on the screen show where the waves were interfering constructively, while the dark areas show where destructive interference was taking place. Let's take a closer look at how constructive or destructive interference takes place by looking at the following diagram. S1 and S2 represent the two slits that are separated by a distance d. Each slit acts like a light source when it's illuminated by a coherent light of a single wavelength or color. When the light, represented by two red lines emitted from the slits, arrive at point P on the screen, interference will occur. If constructive interference occurs at that location, then a bright line appears. If the two beams interfere destructively, however, then a dark line would result. Whether constructive or destructive interference occurs at point P depends on the path length difference between the distances that each wave must travel from either slits to point P. Let R1 be the distance that the wave leaving slit 1 has to travel to reach point P, or R2 be the distance for the wave leaving from slit 2 to travel to reach point P. A wave that is emitted from slit 2 will have to travel a longer distance compared to slit 1 to get to point P. Using simple geometry, it can be seen that an isosceles triangle is formed between points A, P, and C, and that the path difference delta between the distances R1 and R2 is therefore equal to the length between points B and C. BC, however, is also one of the sides of a right-angled triangle of points A, B, and C, with D being its hypotenuse. This assumption is true if the distance between the slits and the screen, L, is much greater than the distance between the two slits, D. So this makes BC being equal to D sine theta, and therefore the path difference delta, R2 minus R1, is also equal to D sine theta. The value of the path difference delta determines whether or not the two waves are in phase with each other when they arrive at point P. If delta is 0, or some integer multiple of the wavelength, then two wavelengths will be in phase with each other when they arrive at P, and constructive interference occurs. So the condition for constructive interference can be expressed as d sine theta being equal to m lambda, where m is some integer multiple starting with 0. M is called the order number. The central bright fringe occurs when m is equal to 1, is called the 0th order maximum. The first order maximum occurs when m is equal to plus or minus 1, and the second order maximum is when m is equal to plus or minus 2, and so on. The plus and minus sign indicate that there are fringes on either side of the central maximum. When delta is an odd multiple of half of the wavelength, then the two waves will be 180 degrees out of phase with each other when they arrive at point P, and destructive interference will occur. So the condition for destructive interference can be expressed as delta being equal to d sine theta, which is equal to m plus a half of lambda, where m is an integer starting from 0. When the distance L is much greater than the slit separation d, then the angle theta is very small. Under this condition, we can use the approximation that sine theta is equal to tan theta, where theta is also the angle of the right-hand triangle PQO. The tangent of that triangle is equal to the distance of the fringe from the central maximum divided by the distance from the slit to the screen. This allows us to obtain an expression for the position y of the fringe relative to the position of the central maximum O by replacing sine theta with y over L and then transposing for y. Using this result, we can see that bright fringes occur at distances lambda times L times m divided by d, and the dark fringes will be located at positions lambda times L times m plus a half divided by d. This result provides an experimental method for measuring the wavelength of an unknown light in a method called spectroscopy. For example, using the Young's double-slit experiment, with the slits being 0.03 millimeters apart and the screen being 1.2 meters from the slits, the second order bright fringe is 4.5 centimeters from the central maximum. So what is the wavelength of the light used? There are many other interference effects that are commonly observed, such as those in the case when thin layers of oil are deposited on top of water, or the varied colors that can be observed in soap bubbles. In summary, interference of light waves occur when two or more waves superimpose at a given point. A sustained interference pattern is observed if the sources are coherent and monochromatic. In Young's double-slit experiment, the path difference for light emanating from two slits and interfering at a point on a screen some distance away is equal to d sine theta, where d is the distance between the two slits. Constructive interference occurs when this path difference is equal to an integer multiple of the wavelength of the light, m lambda, where m is an integer number called the order number. The distance of the bright fringes from its central maximum is given by ml lambda on d, where L is the distance between the slit and the observation screen. The condition for destructive interference occurs when the path difference is equal to a half multiple of the wavelength of the light. The distance of the dark fringes from its central maximum is given by m plus a half of L lambda over d.